In this video, I want to take a look at the differences between first-order linear and general first-order equations, um, related mainly to how the existence and uniqueness theorems apply here. So let's start off with the interval of existence. Both existence theorems say there is a unique solution given conditions, and they state that there's an interval on which that solution is continuous. I want to look at how we find that interval. Right? Start off with a first order linear example here. This is first order linear, although I see I have a t in front of the y prime, so let's divide everything by t to rewrite it this way, the way we normally would. This right here is my p of t, this is my g of t. Notice that p of t has a discontinuity at t equals 0, can't divide by 0. This is actually a hole in the graph. It's not an asymptote, it's a hole in the graph, but still it's a discontinuity at 0. This one definitely has an asymptote at t equals 7. So looking both at p and g, I see a discontinuity. One of them at 0 and another at 7. So I split the line, the whole t-axis now up into 3 pieces, from minus infinity up to 0, and then from 0 to 7, and from 7 to infinity. Right. Now my initial condition that was stated in this problem was that y of 3 is 5. So the t value in the initial condition is somewhere between 0 and 7. So the interval that I'm looking at here, that the interval that's stated in that theorem, is from 0 to 7. Okay? And the theorem says that the solution then will be continuous on the interval from 0 to 7. I don't even have to solve it. I already know that that's where the solution will be continuous. Likewise, if my initial condition was changed to y of 10 is 2, then the 10 is not between the 0 and the 7, it's bigger than the 7, so I'd be going from 7 to infinity, and from 7 to infinity, actually, I guess if I turn it around from you, 7 should be on this side, infinity going that way. But that would be the interval that I would expect to find a solution. Right? I'd be guaranteed to find a solution in that interval that is continuous for the whole thing. Okay. Now, on the other hand, let's look at a nonlinear example. So here's my next example where I've got y prime is minus t over y, with y of 3 equal to 4 for my initial condition. This is not linear because the divided by y here. This function, though, is continuous everywhere except for where y equals 0. So throughout the t-axis, anything above is good, anything below is good. The only problem is you don't want to divide by 0, and that's what's in the denominator. Likewise, if I look at the partial derivative of this with respect to y, it's t over y squared, which again, the only problem here is dividing by 0. So the rectangles where I can be looking are the rectangle which is the top half of the plane or the bottom half of the plane. Right? With my initial condition here with a positive y value, I'm looking at the top half of the plane. That's the rectangle where my function here is continuous and its partial derivative with respect to y are continuous. That contains my initial condition, so the top half of the plane. Now, I'll solve this as a separable differential. No, what am I looking at? Solve this one as a separable differential equation. So I'm going to multiply by y, multiply both sides by dt, and I get this. Integrate both sides, y squared over 2 equals minus t squared over 2 plus a constant. Multiplying both sides by 2, I get this, which, if I slide the t squared over, you'd see this is the equation of a circle. T squared plus y squared equals a constant. Okay? Plugging in the initial condition, t equals 3, y equals 4, I get that c is 25. And in this case, it's not too hard to explicitly solve for y equals by taking the square root of both sides, making sure I take the positive square root, because remember, my y value of my initial condition was positive 4, so I want the positive square root so that my answer is up there in the top half of the plane. Notice that this solution is defined and continuous only from minus 5 to 5. The top half of the circle, the function doesn't even exist out here, but between minus 5 and 5, you've got this function. It passes through the point we want at 3, negative 4. No, 3 positive 4, sorry, 3 positive 4. And it's continuous there. So even though the rectangle that I was looking at to start with was good for t's from minus infinity to infinity, my solution wasn't continuous from minus infinity to infinity. It was only continuous from minus 5 to 5. Okay. Likewise, or sorry, more so even, if I changed my initial condition, keep the t value the same, so it's still 3, but say 8 instead of 4. Okay. Well, then c would be 73, and my function would look like y equals the square root of 73 minus t squared. And now this is defined from minus the square root of 73 to plus the square root of 73, which is a different interval than what I had before. So same t0, same initial t value, but I changed the y value of my initial condition, and it changed the interval on which my solution was continuous. This is very different than the first order linear. First order linear, you look at P and Q, whatever interval contained your initial condition, that's where your solution was continuous. This one, you really got to solve it. You got to go right down to plug it in your initial condition before you can see where your interval is that the solution will be defined on. Next, explicit solutions. First order linear, we always get an explicit solution. That's the way we solve it. We end up with y equals 1 over the integrating factor times the integral of g of t times the integrating factor, right? We get an explicit solution every time. In the nonlinear examples, you don't necessarily get one. Now, this one I happen to be able to solve it, but really it was better to leave it this way, that this is, the solution curves are circles, and a circle is not a function. Y is not a function of t, t is not a function of y. I had to cut it and say just take the top half in order to make it a circle. So really the solution was an implicit function rather than an explicit function. Right? And that's quite often the case when you're solving these general first order equations, that you do not get explicit solutions, but you get implicit solutions. Okay. Now, the last thing I want to look at is the general solution. When we do that first order linear thing and do the integral and you throw a plus c on the end, that plus c on the end is describing all the solutions. You are really getting the general solution. Okay. On the other hand, for the general first order equations, even though we end up with plus c's on these things, it isn't necessarily describing all the solutions. For example, here's an equation, y prime equals y squared. I'm going to see if I can find all the solutions. Right? So this is separable. I'm going to divide both sides by y squared, multiply both sides by dt, sorry, and then integrate. So this is a y to the minus 2, so it integrates to y to the minus 1 divided by minus 1. The integral of dt, of course, is t, and then plus a constant. Now solve for y, so I'll take the reciprocal of both sides, and then multiply by -1, and I get that y equals -1 over t plus c. This is a whole bunch of things that look like that. So I've got a bunch of solution curves shown here. The red one here is with c equal to 4. The blue one is with c equal to 2, and the black one has c equals -3. And for any value of c you pick, the solution curve will look just like one of these things, just shifted over until you have a vertical asymptote at t equals -c. Okay. So for every value of c, you definitely get a solution. However, there are solutions that are not included here. For instance, y equals 0. Y equals 0 is the constant function, which is just the t-axis, right? The slope is 0 everywhere. So if you look at that differential equation that we started with, the slope is always 0 and the function is always 0, and 0 squared is definitely equal to 0. So y equals 0 is a solution of the differential equation, but it is not of the form that we gave. So this is not the general solution. This is just a lot of solutions. Now, by throwing that one in, do we have all the solutions? I think the answer is yes, but it's not obvious at all when you're missing solutions. In The next section will actually look at some other ones where there's multiple solutions that you don't see once you get what looks like the general solution, but we'll be able to pick out those extra solutions as well. Okay, so there you go, the differences between first order linear and general first order.